Hi, in this video, we are going to look at the multiple product of vectors. So this is continuing the series that we have been doing on vectors and 3D geometry. So far we have done scalar product, vector product, and now we go to multiple product. And the first thing that we want to talk about is the scalar triple product of vectors. Scalar triple product. So basically, if you have three vectors, A, B, and C, then the quantity A cross B dot C is the scalar triple product. First of all, you have to realize here that this thing is going to come out as a scalar because cross product here is a vector and it is a scalar product of that vector with another vector that will give us a scalar, right? Dot product with this. So this is my triple product. Now, this is sometimes denoted by A cross B dot C is sometimes denoted by the symbol square bracket ABC. And that is just a symbol for the scalar triple product or box ABC, right? You should know that A cross B dot C will be zero if and only if there are two cases. One case is either one of A, B, or C is a zero vector, right? If one of them is a zero vector, you will get a zero here. And if none of them are zero vector, then C is perpendicular to A cross B. And think about this for a moment. C is perpendicular to A cross B. But you know that A cross B itself is perpendicular to the plane of A and B, right? So if you visualize it on a diagram, this is what it looks like. This is a plane. This plane contains two vectors A and B, right? And the direction perpendicular to A and B both, this is the direction of A cross B, right? This is perpendicular to the plane. Now, if you think about it, C must be perpendicular to this vector A cross B. So if C is perpendicular to A cross B, it should be like this 90-degree with A cross B. So you can see that C vector, you can lift this vector and put it back here and it will completely lie in the plane. C vector is in the same plane as A and B, right? Because it is perpendicular to the normal to the plane. A cross B was the normal to the plane and C is perpendicular to the normal. So C must lie within the plane. So we can say here that A, B, and C are coplanar vectors. If A, B, C are coplanar, then the box product of A cross B dot product with C will be zero. So these are the two ways in which the box product can be zero. Either one of the vectors must be zero or the vectors, three vectors must be coplanar, right? Okay. Now, the next thing that you need to understand here is the geometrical meaning of the scalar triple product. Geometrical meaning. And if you think about ABC as three non-coplanar vectors, ABC are non-coplanar vectors. Then we place A, B, and C as the edges of a parallelepiped. Basically, it's a three-dimensional body. You have one C direction here, one direction is A, one direction is B, right? And you place the three vectors starting from the same point. Then what this means, the box product will actually give us the volume of this figure. Imagine this figure in space. This is like a cuboidal type of a figure, which is known as a parallelepiped. This is the B side, this is the A side. So obviously the area of this base parallelogram, area base is A cross B. We have seen that area of a parallelogram is A cross B. Now, if I want to find the volume, I need to multiply the area by the height, right? So the height of this. So I need the perpendicular height here. So obviously that would be that would come if you do mod A mod B sine theta dot product with the normal vector. Like I need this height, right? So I need this angle theta and I need C sine theta. Actually, I will call it a different angle. Just let me do it. So if this angle is phi, I need C sine phi, which is the height. This was the area of the base, right? Area of base. If I multiply that with C sine phi, I will get the volume of the whole thing, right? And imagine this is the normal vector. This is the vector in the direction of A cross B. So this angle phi is pi by 2 minus this angle. And this angle is the angle between A cross B and C, right? So when I say sine phi, I can write it as C cos of the angle between A and B, because it is cos of pi by 2 minus phi, right? So if you think about it, cos of pi by 2 minus phi is the same as sine phi. So these two things are equal. So now what I need is this quantity, the magnitude of A cross B. So mod of A cross B multiplied by mod of C and cos of pi by 2 minus phi, where pi by 2 minus phi is the angle between A cross B and C vector. So obviously that should be A cross B dot product with C, right? So you should be able to understand here the base is coming by A cross B, the base area of the parallelogram, and the height is actually C sine of the angle between the C vector and the plane of A and B. But that angle is 90 minus theta, where theta is the angle between the C vector and the normal, or C vector and A cross B. So eventually it turns out that it is this A cross B dot C. So what we know from here is that A cross B dot C, which is the box product, is the volume of this parallelepiped, right? So what is the parallelepiped? Basically, you start all the three vectors from the same point and you draw parallelograms with respect to each of these vectors, and you'll get a three-dimensional shape. The volume of that shape will be the box product A cross B dot C. So that is something that you should understand. It is a very important idea. And from here, we can also say that if the volume of this shape was zero, then the C vector must have been in the same plane, right? The only way in which the volume of this figure, the three vectors are coplanar is if the volume of this is zero. So the box product must be zero for it to be coplanar, right? Okay. Now that we understand the geometrical meaning, now we come to some of the properties. So first of all, if A, B, and C are vectors, the first property is the property where the box product is symmetric as long as you don't change the order. So A cross B dot C will be equal to B cross C dot A will be equal to C cross A dot B. But if you tamper with the order, A cross B dot C will be negative of B cross A dot C. So these results are easy to prove. You can take any three arbitrary vectors and prove that these things will be same. So the box product of ABC is the same as the box product of BCA is the same as the box product of CAB. And if you change the order, ABC box product is equal to negative of ACB box product, and so on, right? So this is a very important idea. We'll be using it in many problems. The second point is, if A, B, C are three vectors, then A cross B dot product with C is the same as A dot B cross C, right? So notice that earlier we had written this as, we had written it as BCA, right? So obviously the dot product, we already know that ABC is equal to BCA, right? And now think about it. If you write it like this is the dot product of two vectors. So obviously I can reverse the order of it, right? Dot product is commutative. So this can be written as A dot B cross C, right? So that is the more standard way of writing it. A dot B cross C is your standard way of writing the box product, right? Now, from here, we can also prove things like what is the box product of ijk. You can find this out. And box product of ijk will be 1 because I dot j cross k. And when you do j cross k, what you will get is I itself, and I dot I would be 1, right? So these basic manipulations on the box product you should be able to know, and you should be able to do it yourself. Then the third thing is, if A, B, C are three vectors and L, M, N are three scalars, then what is the box product of L, A, M, B, N, C? The box product. So this will actually become simply L, M, N. All the scalars come out and it is A, B, C. It is very easy to prove. You should look at the definition of the box product. You will write LA dot product with MB cross NC. Now MN comes out from here and you can combine it all and you will be able to show that this is the same thing, right? This is an easy property because it is vectors with scalars. However, sometimes you can write vectors in terms of other vectors or basis vectors. So if A vector can be written as A1L plus A2M plus A3N, right? And B vector can be written as B1L plus B2M plus B3N. And C vector can be written as C1L plus C2M plus C3N. So what are we writing here? Each vector is being written in terms of three vectors, L, M, and N. So you are splitting A in terms of its components along L, M, and N, right? It could be L, M, N, could be IJK, or could be something else. But you need to be able to now calculate the box product of ABC. Box product of ABC, you can prove will be equal to the determinant of A1, A2, A3, B1, B2, B3, C1, C2, C3. And this determinant is multiplied by the box product of L, M, and N, the basis vectors. Okay, so we will do a proof for this. This is a very important result that will be used many times. So let's try and do the proof. So here, when I want to find box product of ABC, what I need to find is A dot B cross C. So first I will try to calculate here B cross C. So B cross C would be equal to, we have seen vector products when B was written as B1L plus B2M plus B3N. We have seen a property like this in vector product also of two vectors, C2M plus C3N. So we can write B cross C as L cross M, M cross N first, M cross N cross L, and L cross M, and this is B1, B2, B3, and C1, C2, C3. If you are not sure of this determinant, just expand it and calculate B cross C directly. How do I calculate it directly? You will just do this cross this cross this cross this, and all 9 terms. 3 of those terms will vanish and you will end up with 6 terms. And finally, you can prove that B cross C will come out to be equal to M cross N multiplied by B2 C3 minus B3 C2 minus N cross L, and here you have B1 C3 minus B3 C1 plus L cross M, and you have B1 C2 minus B2 C1. So this is my B cross C, and now I have to do A dot product with B cross C, right? So A vector itself is A1L plus A2M plus A3N, right? And I want to do dot product with B cross C here, and B cross C I have written in terms of these things, right? So notice that when you do L dot M cross N, that will give me the first term. So I will get L M N box product, and I will get A1 into B2 C3 minus B3 C2, right? Then I do L dot this, it will be 0, because when you do box product of L with N cross L, that has to be 0 because this vector is perpendicular to L vector, right? So this will be 0, and when you do L with L cross M, that will also be 0. Similarly, now you do M this part with this, it will be 0, but this part with this will not be 0. It will be minus MNL box product and A2 B1 C3 minus B3 C1. And finally, you will have a with A3N here, you will do it with this one. It will be a plus NLM, and that would give us A3 B1 C2 minus B2 C1, right? And now you can see that LMN is same as MNL. So LMN is same as MNL, and that is same as NLM, right? So here we can okay, here we can take LMN common, the box product, and what we will end up getting LMN box product common. All 3 are actually same. So we can take it common and you will end up getting this minus this plus this, which is basically the determinant that I was talking about. You can show that that is equal to the determinant of A1, B1, C1, A2, B2, C2, and A3, B3, C3. So that determinant times LMN, box product, is equal to ABC. Here A, B, and C were written in terms of the vectors L, M, and N, right? And A1, A2, A3 were the components of A, B, C in terms of L, M, and N. Actually, the determinant was like this. A1, A2, A3 were in rows. A1, A2, A3 was in rows, B1, B2, B3, and C1, C2, C3 was like this. So to understand the usefulness of this property, let's try to do at least one problem. Let's look at this question. You have to show that the box product of 2A plus B plus C, A plus 2B plus C, and A plus B plus 2C is equal to 4 times ABC. Now, There are many problems like this that you will encounter. So what I want you to think here is, let's call x vector as 2a plus b plus c, y vector as a plus 2b plus c, and z vector as a plus b plus 2c, right? Now here x, y, z vectors are being written in terms of the three vectors a, b, c, and I want to find box product of x, y, z, right? If you want to find box product of x, y, z, according to the method that we just now saw, I will write it as a determinant. Components of this will come on the first row, 2, 1, 1. Then components of this, 1, 2, 1. And then components of this, so 1, 1, 2. This determinant times the basis vectors, which are a, b, c. You are writing x, y, z in terms of a, b, c. So we can write this. And when you calculate this determinant, let's see what comes. So this is equal to 2, and this is 4 minus 1. So 3 minus 1, and this is 2 minus 1. So 2 minus 1, and plus 1 into this is 1 minus 2. So minus 1. So this is 6 minus 1 minus 1. So it is clearly 4. So this determinant is 4, so therefore you are able to prove this is 4ABC, right? So otherwise, if you wanted to actually prove it in the longer way, you would have to do the definition of this. You would have to do something like this: 2a plus b plus c dot product with a plus 2b plus c cross product with a plus b plus 2c. Now, simplifying this and proving that it is 4ABC box product is also possible, but it will definitely take longer time. So I want you to understand what property we have just now seen and how to apply that. This is a very useful property in problems. So keep that in mind. Okay. Now, another related theorem, we can say, let A, B, C be vectors of magnitude A, B, C, and A dot product with B so we are given this information. A dot B is alpha, B dot C is beta, and C dot A is gamma, right? Then I want to prove that box product of ABC square is equal to A square, B square, C square, and determinant 1 cos alpha cos gamma, cos alpha 1 cos beta, and cos gamma cos beta and 1. Okay, so how do we do this? What you can see here is A, B. Okay, so actually these are the angles between the vectors. I made a mistake here. It is not dot product. We know the angle between the vectors. Angles between A and B is alpha, B and C is beta, and C and A is gamma. So ABC are vectors of magnitude ABC. Angle between the vectors is alpha, beta, gamma. So what I know is that A dot B is going to be AB cos alpha. B dot C is going to be BC cos beta. And C dot A is going to be CA cos gamma. These are the three things that we know, right? Now, let's think about how you would do this. So this is going to be box product of ABC times the box product of ABC. And these are both scalar quantities, right? So what we can say here is this is the product of two determinants, and by determinant multiplication rule, you can write it like this: A dot A dot B, A dot C, and this will be B dot A, B dot B, B dot C, and C dot A, C dot B, and C dot C. This is what will come. And that is coming by the determinant multiplication rule. If you do the product of two determinants, this is what will come. And from here, we can say that this quantity will become what? This quantity will become A square, AB cos alpha, AC cos gamma, AB cos alpha B square, BC cos beta, and AC cos gamma, BC cos gamma, and C square. And then if you take A square, B square, C square common, you will end up getting this. Take A common from the, you can take A common from the first row. A can also be taken common from the first column. So you'll get A square. Then you can take B common from the first row, second row, and also from the second column. You'll get B square. So if you simplify it, it will come out to be this. Okay. Now, why is this going to be useful? Because this tells us this general rule. If you have box product of A, B, C with another three vectors L, M, N, you should remember that this will come out to be this determinant A dot L, A dot M, A dot N. So we are doing A with the first row, and that is the first row of a determinant. Then it would be B dot L, B dot M, B dot N, and finally it will be C dot L, C dot M, and C dot N, right? You can see why this is true, because if LMN was IJK, suppose it was IJK, then you are doing box product of ABC with IJK. And according to this rule, it is coming out to be A dot I, which is the A1, which is the I component of A. Then it is A dot J, which is A2 and A3. And similarly, you get B1, B2, B3, and C1, C2, C3. And this is actually the way to calculate box product, because box product of ABC, IJK, we saw box product was 1, right? So this is equal to this. Here, what we have said is A is A1I plus A2J plus A3K. And B is B1I plus B2J plus B3K. And C is C1I plus C2J plus C3K. So if ABC are written in form of IJK, we know box product can be calculated like this. You can check this out yourself by following the definition of A dot B cross C. Calculate it and you will see that it is this determinant, right? So now what we are doing is, instead of doing this, we are putting L, M, N here. Notice that A1 is what? A1 is A dot I. This is what? This is A dot J. This is A dot K. This is B dot I, B dot J, and B dot K. And this is C dot I, C dot J, C dot K. So technically, if I replace IJK with another vector LMN, I am doing that only A dot L, A dot M, A dot N, and so on. So remember this property. This property is going to be useful for you in problems. So now, obviously, if I replace this with A, B, C, and another A, B, C here, right? Then it will become A square, A dot B, A dot C, B dot A, which is same as A dot B, B square B dot C, C dot A, which is A dot C, B dot C, and C square, right? And that is what I used in the previous screen. So this should explain that result which we saw previously, right? Okay. So remember this general way of multiplying two box products. That is what you should take away from it. If you know this, you can apply it in different problems appropriately. This is A dot L, A dot M, A dot N, and similarly B dot L, C dot L, B dot M, C dot M, B dot N, C dot M. So when you use it appropriately, remember this result for sure, right? Now let's move on to other types of properties. We have this result. If A, B, C are three vectors, then A cross B plus C is same as A cross B plus A cross C. And okay, this is simply the associative rule. So we have already seen it. I'm just writing it for reference purposes. This will be B cross A plus C cross A. And next we have the idea which we have already discussed, that three non-zero coplanar vectors, three vectors ABC are coplanar if and only if their box product is zero. The next new idea that we want to talk about is the volume of a tetrahedron ABCD. Volume of a tetrahedron ABCD. Okay. So a tetrahedron is usually a figure with four sides. There is a side here that is behind. So you can label it like this: A, B, and this thing is into the plane here, C, and this top one is D, right? So the way to find the volume of a tetrahedron is technically by finding the same method as before. Find area triangle ABC. That should be half of AB vector cross AC vector, right? Okay, now we have to multiply the, now we have to basically try to take the volume of this whole shape, right? But the point is that just like in a cylinder, when you take a volume, you do pi r square h, right? But in a cone, when I take the volume, I do 1 by 3 pi r square h, right? Because there are three possible cones that can be fit into the same cylinder. Just like this here, what I want to find out first is the height of this height h. So the component of AD vector along on the normal to plane of ABC, right? The normal vector is in the direction of AB cross AC, right? So we need the component of AD, which is this vector along the normal direction, right? So that can be done by doing dot product, right? So I want to do AD dot the normal vector and divide it by the modulus of the normal vector, right? So basically it is AD dot product with the normal unit vector. That will give me the component, required component, right? Now, if you think about it, the normal vector, the unit vector in the direction of the normal is along AB cross AC itself, right? So what I have here, this is the magnitude of the area. The total volume will be 1 by 3 times 1 by 2 AB cross AC, the magnitude of this area multiplied by AD vector in the direction of the normal, right? So technically, this normal unit vector is in the same direction as this, right? So I can write this as 1 by 6. And now remove the modulus because the magnitude and the direction are both present. And this becomes AB cross AC dot product with AD, right? This becomes your volume. So this is the same thing as 1 by 6 AB AC AD box product. So what are we doing here? We are saying find the area of this triangle and 1/3 of that area times the height will give us the volume of this tetrahedron. Okay. So the way we do it is the height comes as AD dot n unit vector, and you have to do magnitude of the area times AD into n unit vector into 1/3. So this becomes 1/6 and AB cross AC dot AD vector, right? So that is the box product. So basically, if you have 4 vertices of a tetrahedron ABCD, the volume is 1 by 6 box product from one of the vertices to the other 3, AB, AC, AD. That becomes your volume of the tetrahedron. Remember this result? Now, if instead of the 3 vectors, either you know the 3 vectors or you can be given coordinates of the points. If you know the coordinates of 4 points are given. From those 4 points, I can find the vectors AB, AC, and AD by doing position vector of B minus A and C minus A and D minus A. Here, A, B, C, D are position vectors of those 4 points. A, B, C, D are position vectors of capital A, B, C, D. Once we know position vectors, we can find these 3 vectors for the sides of the tetrahedron, and then you do the volume by doing 1/6 of the box product. So remember the idea what we did to find the volume. Again, we can now show that these 4 points A, B, C, D, 4 points are coplanar if the box product of AB vector, BC, AC vector and AD vector is equal to 0. Because if the box product of AB, AC, AD is 0, then obviously the tetrahedron formed by them has volume 0, which means they are on the same plane, right? So remember these ideas. The next thing that is an application of scalar triple product is the vector equation of a plane. Vector equation of a plane. So here, if you have a plane passing through 3 non-collinear points, having position vectors A, B, and C, right? So there are 3 points non-collinear having position vectors A, B, and C. Let's say this is my origin. So this is my A vector. This is my B point. This is my C point. This becomes my B vector, and this becomes my C vector, right? How can we say that? How do we form the vector equation of a plane, right? So we can say that there can be a random point on the plane P whose position vector is R. So this vector is my R, the random point on the plane. And we can say that AP vector, AB vector, and AC vector must be coplanar. If all 4 points are in the same plane, we can say that AP, AB, and AC are coplanar. You can do any other order as long as you involve all the 4 points. So we can also say, for example, PB, BC, and BA. Those three vectors are also coplanar. There are many other combinations that you can do. CP, CA, and CB. These three vectors are also coplanar. And now for the condition of coplanarity, I can say that the box product of AP, AB, and AC must be 0. Now what is AP vector? It is R minus A, box product with B minus A and C minus A is equal to 0, right? And we can simplify this, and if you simplify this correctly, you will get the equation of the plane. So let's do that right now. So we will get R minus A dot product with B minus A cross C minus A is equal to 0. So let's calculate this. This is B cross C minus B cross A minus A cross C, and A cross A will be 0. So you have R minus A dot product with this is equal to 0. So we have R dot B cross C minus R dot B cross A minus R dot A cross C minus A dot B cross C, and A dot this and A dot this will be 0. So is equal to 0. So what we can write this as R dot B cross C plus R dot A cross B. And this also can be reversed, C cross A with a minus sign. So plus R dot C cross A is equal to A dot B cross C, right? So the vector equation is coming like this: box product of RBC plus box product of RAB plus box product of RCA is equal to the box product of ABC. This equation becomes the equation of a plane passing through three non-collinear points with position vectors A, B, and C. Understand the theory by which we found this. Don't try to remember any equations here. It is pretty easy what we have done, and you should get the idea behind what we did. Okay, let's do an example here. Find the equation of the plane. Find the equation of the plane through the points A, which is 1, 2, 1, 3, B is 1, 1, 2, and C is -1, 2, 4. We need the vector equation of the plane through these points. So what I will do is do the same thing that we did before. We'll say, let's say P, which is x, y, z, is another point, right, on the plane. And we have A, B, C are three other points on this plane, right? So obviously I can say AP vector, AB vector, and AC vector are coplanar. AP, AB, AC are coplanar, right? So what I will get is AP is going to be x minus 2 I cap plus y minus 1 j cap plus z minus 3 k cap. This is my AP vector. What is my AB vector? Is going to be B minus this. So it is minus 1 I cap plus 0 j cap minus 1 k cap. This is my AB vector. And finally, AC vector is going to be minus 3 I cap plus j cap plus k cap. This is my AC vector. So these three vectors are coplanar, means the box product of these vectors will be 0. So box product of these will be the simple determinant x minus 2, y minus 1, z minus 3, minus 1, 0, minus 1, minus 3, 1, 1. This determinant should be 0. for it to be coplanar. So if you evaluate the determinant, you will get the equation x minus 2, and you have 0 minus minus, so plus 1, minus y minus 1, and you got minus 1 minus minus minus, so minus 3, so minus 4, plus z minus 3, and you get minus 1 here is equal to 0. So we get x minus 2 plus 4y minus 4 minus z plus 3 is 0. So x plus 4y minus z is equal to 4 plus 2, so 3. So this becomes your equation of the plane in this case, right? So it's a very simple idea as long as you understand coplanar, what is the meaning of coplanarity, right? So right now we have found the equation of a plane passing through 3 points. Now we do another form of the plane equation. Plane equation passing through a given point, and with position vector A, and parallel to B and C, is what? So here, basically, the plane passes through a particular point and is parallel to B and C, right? So if you have a plane like this, A is a point on it. This is my A vector. This is a point on the plane. Let's take another random point on the plane. This is R vector with reference to the origin, right? There are two vectors in the plane, B and C. The plane is parallel to these two vectors. So we already have two vectors in the plane. Remember, in the previous case, we had three vectors in the plane, right? And we said that if you can make three vectors in the plane, then you can say that the three vectors are coplanar if their box product is 0. Now, here the plane is passing through a point, and there is a random point in the plane at R. So we can make a vector here, R minus A vector, right? This is also a vector in the plane, and since it is in the plane, it will be parallel to B and C. And therefore, we can say that the box product of these three vectors must be 0. The box product of these three vectors must be 0. Then only we are getting the three vectors are coplanar. So if you simplify this, this can be written as RBC is equal to ABC also, right? Or you can just write it like this, R minus A dot B cross C is 0. So that is another way to write the plane equation here, right? So we have first seen plane equation passing through 3 points. Then we saw plane equation passing through 1 point and parallel to two vectors. We can also do the last remaining case, plane through 2 points, A and B, and parallel to C vector. Again, the method is same. Take a third point R vector in the plane, make three vectors AP, AB, and say C are coplanar, right? The AP vector will be R minus A, AB vector will be B minus A, and this will be C. So you'll get something like this, R minus A, B minus A, C. Box product is 0. And this will become finally, after simplification, RBC box product plus RCA box product is equal to ABC box product. This is what you will finally end up getting. So the ideas for all of these are similar. So you should not be too confused by these things, right? Now, the next idea that we want to talk about is the idea of skew lines. So what are skew lines? So the definition is two straight lines L1 and L2 are said to be skew lines if there exists no plane, if there is no plane containing both these lines, containing both these lines. So these two lines cannot be put in the same plane. They are such lines which are not coplanar to each other, right? So what we can say, two properties that you should know is that no two skew lines can intersect each other, because anytime two lines intersect, they have to be in the same plane. But there is no such plane for two skew lines. There is no such plane exists, right? So they can never intersect, correct? So no two skew lines can intersect each other. Then the other thing is no two skew lines are parallel to each other. Because if they are parallel to each other, then obviously there is a plane that is parallel to both of them, right? So then the two lines will be lying in that plane. So the skew lines are such lines which are neither parallel and they neither intersect. That is the slightly weird thing that you see here, right? Okay. Now, the first thing that we have to do about skew lines, the first theorem is this one. Let L1 and L2 be two skew lines. Then there exists a unique point P on L1, a unique point P on L1, and a unique point Q on L2, such that PQ vector is perpendicular to both L1 and L2. So you can find 2 points P and Q on the skew lines in such a way that the segment PQ is perpendicular to both of those lines, right? So how do we do that? So we say let A be a point on L1 and B be a point on L2 such that OA vector from the origin to A is A vector and OB vector is B vector. So the position vectors of A and B are small a vector and small b vector, right? Now let B and D be non-zero vectors, parallel to L1 and L2 respectively. So your B vector is parallel to, I should write it as a small vector form. So I will say let small b vector and small d vector be non-zero vectors parallel to L1 and L2 because we have to specify the line's direction, right? So vector equation of L1 would be R is equal to A plus T times B vector, and L2's equation would be R is equal to B plus S times uh, Okay, I have made a mistake here. Obviously, I have used B vector here, so I cannot use B and D here. I have to use C and D. C and D are the directions parallel to L1 and L2, right? So the equation of line L1 would be R is equal to A plus T times C vector, right? And equation of line L2 would be B plus T times B plus some constant, and that constant can be given the name S. So a scalar times D vector, right? These are the equations of my two lines. And now, since L1 and L2 are skew, since L1, L2 are skew lines, we can say that they are non-parallel. They are not parallel. So one thing you can say there is that C dot D will not be equal to mod C mod D, right? That is something that we know is not true. Now, what we have to find is 2 points, the intersection of these two lines, right? They are non-parallel. So we need to find 2 points P1, P and Q on these lines. So let's say let P and Q be 2 points on L1 and L2 such that we can say OP vector would be A plus T1 times C and OQ vector would be B plus S1 times D, right? So this P lies on line 1, this is on line 1, and this is on line 2, right? Now PQ vector, the segment would be B minus A plus T1C minus S1, B minus A plus S1D, S1D minus T1C. This is my PQ, and we have to show that PQ dot C is 0 and also PQ dot D is 0, because we have told that PQ is perpendicular to both lines, right? So basically, if you use this equation that PQ is perpendicular to both lines, you will be able to find S1 and T1. You have to solve that equation. So what are the conditions that are coming? Notice you will get PQ dot C. So it will be B minus A dot C plus S1 D dot C minus T1 C square is 0. And another equation would be PQ dot D. So B minus A dot D plus S1 D square minus T1 C dot D is 0, right? From these two equations, we have to find S1 and T1, okay? So if everything else is known, A, B, C, D vectors are known, you can find S1 and T1. And if you find S1 and T1, you will be able to find the location of OP and OQ. And that will be your line segment that is basically perpendicular to both of the skew lines, right? Okay, now why is this important for us? Why do we need to figure out this? So when we talk about the shortest distance between two lines, we mean this line segment PQ. It is the modulus of this vector PQ, which is such that PQ is perpendicular to both L1 and L2, and P lies on L1 and Q lies on L2. So if we find the length of this PQ, that becomes the shortest distance between two skew lines, right? If the lines were intersecting, if the lines are intersecting, and then that means that they are not skew lines, then the shortest distance mod PQ would be 0, because since the lines are intersecting, P and Q can be on the same point, right? So now that we know the meaning of skew lines and the meaning of the shortest distance, we can prove the formula for the shortest distance between two skew lines. So the shortest distance between the skew lines R is equal to A plus TB and R is equal to C plus SD is given by mod of A minus C dot product with, no, it's not, it is a box product, but box product of A minus C, B and D, this box product on top divided by mod of P cross T. So the whole thing is taken as a mod as well, right? So let's try to prove how we come to this formula, right? So let P be on line R is equal to A plus TB and Q is on line R is equal to C plus SD, right? Such that PQ is shortest distance. So that means PQ is perpendicular to L1 and L2, both the lines, right? So let's say A and C be points such that OA vector is the point A vector and OC vector is the point C vector. So we know that A lies on the first line and C lies on the second line, right? Now, B vector is parallel to line 1 and D vector is parallel to line 2. That is given from the line equation only. So far, whatever I am saying is coming from the meaning of the line equation itself, right? Right. Now, B is parallel to line 1, D is parallel to line 2. So, B cross D would be perpendicular to, this implies B cross D is perpendicular to both B and D. And what other line is perpendicular to both B and D? PQ, right? So that means B cross D is parallel to PQ, right? That is something that you should conclude from here. So if B cross D and PQ are parallel to each other, then we can say that the unit vector in the direction of PQ, vector is simply B cross D divided by mod of B cross D. This is the unit vector in the B cross D direction, right? Now all we have to do is find the component of AC on PQ, because you have to realize that A and C are points on the line. A and C are points on the line. I need the shortest distance PQ. So I need the component of AC vector on this PQ, which is in the direction of B cross D by mod of B cross D, right? So this vector is C minus A, and we have to take the component of C minus A along this vector. So by the theory that we have learned so far, that would simply be C minus A dot product with B cross D by mod of B cross D divided by the magnitude of the second vector, which is 1, right? So this should come out to be the length. If you take the modulus, this will come out to be the length, right? And basically that is the formula. A minus C box product with B and D, whole thing divided by the magnitude of B cross D. And the whole thing is taken as a modulus. That becomes the length of the skew line, right? The shortest length of the shortest distance between two skew lines, right? So that is something that you should understand. Conceptually, it is not very difficult to figure out. The next point is angle between line and plane. Line and plane. And this is pretty easy. If the line equation is A plus lambda B and the plane equation is R dot N is equal to D, right? Then the plane is like this. The normal to the plane is this N vector, and the line could be like this. The line is along the B vector, right? So if you do the dot product of N dot B, you will get this angle, right? This angle, if I call this angle as phi, so cos phi should be N dot B divided by mod N mod B, right? Once we find cos phi, the required angle between the line and plane is simply pi by 2 minus phi is equal to angle between line and plane. Because right now what we have is the angle between the line and the normal to the plane, right? So pi by 2 minus phi, so it is pi by 2 minus cos inverse of this, so that is sine inverse of n dot b by mod of n mod of b. That is your angle between the line and plane, right? So you should know that. And now finally we come to vector triple product. Vector triple product. Okay, so triple product, what is the meaning? It is A cross B cross C, right? So obviously this is a vector, this is a vector, so the answer is going to be a vector. That's why it is called a vector triple product, right? Now, when is this going to be zero? Let's analyze that case. A cross B cross C is zero. What are the conditions? Any one of A, B, C is a zero vector. The second condition is B is parallel to C. If B is parallel to C, then this part becomes zero. And the third condition is A is parallel to B cross C, which means A is perpendicular to both B and C. So if A is perpendicular to both B and C, then it will be parallel to B cross C, and the angle between this and this vector is zero, so cross product of those two will be zero. So these are the conditions when the vector triple product is zero. The next thing is the basic theory of how to simplify this. So if A, B, C are any three vectors, then first of all, you can say A cross B cross C will be equal to A dot C B minus A dot B C. And if I wanted to find what is A cross B cross C, How do I do it? I will only remember this one formula. Don't try to remember multiple versions. This can be written as minus of C cross A cross B. And then you can write it as minus of C dot B A minus C dot A B. And that becomes basically C dot A B minus C dot B A. And that becomes your result for this case. But I don't try to remember that. We just get it from the basic formula for simplification, which is this. You need to remember this. And the proof of this is easy only, and it is there in standard books. I will not do the proof right now because of a lack of time. But if you are interested in the proof and don't understand the proof, I can show it to you in a future video. Okay. The next thing that I wanted to discuss here when you have triple product is, so in triple product, always you need to take care of the order in which the vectors are being multiplied, because it's a vector triple product and order matters everywhere. So use this for simplification and try to simplify it in a step-by-step manner. Some other types of products that we need to know also are scalar product of four vectors. Scalar product of four vectors. So what is this? So this is basically A cross B dot C cross D. This is the scalar product of four vectors. And I want you to just remember this result. This comes out to be A dot C times B dot D minus A dot D times B dot C. Another way to remember it would be simply by this determinant AC AD and BC BD. So remember this determinant. This is the scalar product of four vectors. Okay. Now, this is a result that you can prove. Take A, B, C as any four arbitrary vectors, and it is very easy to show that this result is true. However, you will not have time in the exam to prove it. So I would recommend that you try to remember it, because in case this ever comes, it is tricky to simplify if you don't know this. Okay. So basically try to remember this result and it will be useful for you. The proof of it is take ABC as A1, B1 in terms of IJK and just try to calculate it. You will understand why this is correct. Okay. The next thing, in case you have a vector product of four vectors, what do you do then? So we have, let's say, a situation like this: A cross B cross C cross D. How to handle this? So basically what you should do here in this case is think of R vector, think of C cross D as a R vector, right? And then simplify first this thing, make it a triple product. It is like this now, right? How do we simplify this triple product? It is minus of R cross A cross B. How do we simplify this? So it is minus, according to the formula, R dot B A minus R dot A B. So this basically this becomes R dot A B minus R dot B A, right? And R dot A, what is that? So that is basically C cross D dot A. So that is a box product, right? And R dot B would be C cross D dot B. That's also a box product. So this is CDA box product B minus CDB box product A. And that is the simplification that you needed. Okay. So we have proved that we have written it in this way. So also, by the way, if you had taken A cross B as your R vector, you would get a different form for it. So think about it. Right now we chose this as our R vector. We got the vector product in this form, right? If you do the opposite thing, you take A cross B as your R vector, you will get R vector cross C cross D. So you will end up with R dot C D C minus R dot C D. And that can be written as now R vector is AB. So it is ABD box product C minus A cross B. So ABC box product D, right? So notice that actually this quantity and this quantity are the same thing. And you have two different looking versions of the same vector product of four vectors. So in a multi-correct question, you could have this thing being written either as this or either as this. Both are correct and both are easy to get. So don't get confused about how we are getting all of this and how we are getting two different forms of all of this, right? So that's about it for the theory of multiple products. So we saw scalar triple product. We did a lot of applications, vector equations of plane on different cases. Then we talked about skew lines. And finally, we looked at vector product of three vectors. And in the four vector case, we did scalar product of four vectors and vector product of four vectors. Vector product of four vectors is pretty easy. Just think of it as a three vector situation and simplify accordingly. Scalar product of four vectors, you should remember the formula that I gave you for A cross B dot C cross D. That is something that you need to remember because you will not be able to prove it in the exam. So with that, we come to the end of the theory for multiple products. What I will do is another session where we'll discuss some questions and we'll do some typical examples. And hopefully that will help you consolidate and revise everything that we have learned today. That's it for this video. I'll see you next time.